The floor
Okay.
is all yours, I see.
Yeah. So, I actually remember meeting Demetris sometime in 2010 in Taormina for the Statistical Hydrology Conference. And I had written a reply to his random walk on water paper. And that was a very nice discussion. I was kind of incited by my professor to write this reply. And yeah, we took it very well. And we discussed, and I was very obsessed by Jane's book, the Logic of Science, Probability, the Logic of Science. And I was a bit shocked that Demetris called it partially opinion, partially fact. So that's my memory of my earliest interactions about this topic with you, Demetris. So I'm starting to get convinced by at least this disagreement with this quote you had in the paper. So we'll get to that. I must say I'm a little bit loaded with teaching still. So I probably need your help, Demetris, for some of the explanations. I didn't get to dive in as deep as I hoped to. But in my opinion, the key ideas of the paper are that both thermodynamic and stochastic or statistical approaches to hydrology can be viewed in one single entropy framework. So with stochastic and statistical entropy, or stochastic and statistical approaches, we think about information and information theory. So that's what we usually discuss in this group. So most people are at least quite familiar with those concepts, but maybe a bit less with thermodynamics, at least speaking for myself. And the idea is basically that the principle of maximum entropy can be applied to both deductive and inductive inference about complex systems. And that even the thermodynamical entropy can actually be interpreted as purely a description of uncertainty, despite the unit that's traditionally attached to it. So some examples are given in the paper, and this is not an exhaustive list, but basically from maximizing entropy, you can derive the gas law and the Clausius-Clapeyron equation for vapor pressure, but also the statistical processes like persistence in time series follow from somewhat unintuitively, but they can still follow from maximizing entropy. So first, a bit of background about how these two concepts became, in a way, two different concepts, but still similarly named. And then maybe in the end, they turn out to be the same. So Shannon was actually working on this theory of communication and figured out this this formula for uncertainty based on 3 desiderata for such a measure, totally unrelated to thermodynamics. And some people actually speculate that Shannon was not very aware of the thermodynamic entropy at the time. But then when he chatted to John von Neumann, von Neumann basically suggested to use the name entropy for 2 reasons, because the uncertainty function has been used in statistical mechanics under that name already. So that's the Boltzmann type of entropy, the statistical thermodynamics. And then in the second place, no one knows what entropy really is. So in the debate, you'll always have the advantage. So I'm not sure. Maybe I should take a poll to see if there's anyone who thinks that knows what entropy really is. I still count myself not completely sure what entropy really is. But entropy is winning. That's what I know. So it's better to be on entropy side because it's always increasing. Yeah, so this is actually the quote where Jaynes kind of warned against mixing up information entropy and thermodynamic entropy. So he called it a problem in the field that many people kind of equate them and then reach flawed conclusions. And I'm not sure what papers he looked at, but I think more and more, I think we can regard them as the same concept if you're a little bit careful about the definitions. And that's what I think Demetris did very well in this paper. So one of the things that comes, that's discussed in the paper is actually the principle of maximum entropy. And that basically says that given some limited information, typically in the form of some constraints on macroscopic variables or on some statistics of the stochastic process you're looking at, it's sensible to assume the maximum amount of uncertainty you can achieve while still meeting those constraints. Because if we wouldn't do that, we're actually secretly adding some extra information because we're decreasing uncertainty without the information to back it up, because we have the constraints and that's supposed to cover all information. So if we wouldn't maximize entropy, then we're implicitly adding some information to our inference. So yeah, in a thermodynamical system, that's also true. So if we don't know what all the microscopical particles are doing, it's safe to assume they're trying to maximize uncertainty because that follows from just the laws of probability. So they try to occupy all possible states, and then the states that are most frequent, the total states of the system that are most frequent tend to be associated with maximum uncertainty. But then I think one of the questions I have is, how do you decide what constraints you can use? Because of course, if you maximize uncertainty given some constraints, then the solution depends on those constraints. So typically in thermodynamics, it's some knowledge about the momentum or the energy of the total system. But yeah, maybe I'm wondering why wouldn't you add others? So it seems that you can derive the solution, but what guides the choice of which conserved quantities you use? But we'll get to the questions later. So I'll do this quick introduction and then I'll just walk through the paper. I'm not sure, Leila, what is the optimal time to spend on the presenting part?
I think 30 to 40 minutes is okay. So we can allow at least 30 minutes or more for discussion.
Yeah, okay. Yeah, so that's the principle of maximum entropy. Then, and that's kind of in the information sense. And then if we translate it to thermodynamics, instead of constraints on some statistics about the stochastic process, we're talking about some macroscopic quantities like energy, temperature, momentum. So those are then the constraints. then it's sensible to assume the maximum uncertainty of the microstate of the system. And if not, we're assuming constraints that we should see on a macroscopical level, so we might as well include them. So of course, if you have an incomplete description of what you know macroscopically, then probably you have too little constraints to put on the system. Your solution will be different from what you observe. So then you know you miss some constraint, and like you can try to find what that constraint is. And then once you've used all the constraints, you've kind of exhausted all knowledge that you have on a macroscopical level about the system, and then you should get good predictions about the statistical behavior of the thermodynamic system. And actually a nice effect is that, well, all these microscopical particles are acting crazy. Actually, the system as a whole, in terms of the macroscopic variables, often behaves quite predictable. And Demetris argues that that's thanks to uncertainty at this micro scale, we get this certainty at the macro scale. Yeah, so basically we can ask the question, like, are thermodynamic and information theory really somehow the same concept? Maybe we can see it as that if we lose track of the energy into the microscopic states and cannot say much about them anymore on a macro level, then our uncertainty is basically increasing. And that's maybe the same as that we limit our ability to extract work from those systems in a macroscopic sense. So in a way, the free energy decreases, and you kind of lose that the energy is still there, but it's trapped in this microscopic unpredictable patterns that you cannot use. So this question of whether you can infer the behavior of the statistics of a microscopical system based on a few macroscopic constraints, I think implicitly in there is that we assume that the system is in equilibrium, so a gas that entirely fills the chamber. Like I was thinking about a scenario where you have a gas chamber or like a volume of gas that's divided into two parts. You have all the gas on one side, then you lift the divider, and then you take a quick snapshot of it. In that case, probably any maximum entropy inference about distributions won't work. Like, let's say it's just a few microseconds after you do that, so all the gas is still on one side. So in that case, your macroscopic variables don't tell you exactly what the microstate is, but you're pretty sure that after a short time, the system will go to this equilibrium where you can actually say things about it, just because it's more probable. Yeah, and again, what would happen if you add too many or too few constraints macroscopically? In one case, if you have too many, then probably you're assuming some things apply to the system always. I think if you derive those constraints from actual measurements, then probably you're still doing well, because those constraints might not be binding. Like, they might be satisfied, but they're not essential because the system is already behaving the same way under the other constraints. But maybe if you pick some statistic that's actually fluctuating and you set it as a constraint, then you deviate from the actual correct inference. too few constraints basically gives a too high entropy, and you're missing some predictable behavior. So that's kind of my take on the main things I learned about this relation between the two things. Now I suggest we walk through the paper. Actually, one of Koutsoyiannis' previous papers was called A Random Walk on Water, but right now it's definitely not a random walk because it's actually very nicely organized in a pedagogical order. So we can just walk linearly, and we don't walk on water, but we walk towards water because we start with more general concepts and then build up to deriving some water-related insights. So let me see. Oh. Oops. Can you now see the PDF? Yeah.
Yes, we can.
Okay. So yeah, so the abstract we kind of talked about, but maybe what I forgot to mention is that that one of the applications that is shown is the Clausius-Clapeyron equation from scratch. So that was quite interesting. So we're maybe starting with this question about or this history of entropy. So as usual with Demetris's papers, he educates us about the Greek origin of many of the terminology that is used. So in this case, entropy is somehow related to transformation, and actually Demetris argues that entropy is the driving force of change, because we're always driven to more probable states, and that's what keeps things going. So it was originally introduced in thermodynamics, mainly by people trying to work on getting steam engines more efficient and running into some trouble with that. And basically the thermodynamic entropy classically is defined as that the change in entropy is the change in heat divided by the temperature at which that change occurs. There's some caveat there because actually that's for reversible processes, and actually most processes are irreversible. So in practice, the change in entropy is larger than this one. But then, since we use this to define a reversible process versus an irreversible, the definition is kind of circular. So that was an interesting observation. Then yeah, so later the thermodynamic entropy got a more statistical basis by Boltzmann, who related it to probabilities of microstates in a way, or maybe not yet probabilities, but the number of possible microstates, and then later refined by Gibbs and von Neumann in quantum mechanics. And then Shannon came along from an entirely different angle, trying to quantify information transfer over noisy cables, and deciding how many questions you need to ask before retrieving some message. And then Jaynes, that's some work on connecting the two and actually came up with this principle of maximum entropy. So he basically proposed that this principle of maximum entropy, which we see in thermodynamics, is actually an inference tool that you can use more widely for any guess about probabilities based on some limited information in constraints. So here's this quote, and Demetris actually notes that one of the arguments against seeing the connection between these two is that they're in different units. So actually the information entropy is in bits, but that's kind of unitless. It's a number of questions, but it doesn't really have a unit. While the thermodynamic entropy is in joules per Kelvin. However, he goes on by demonstrating that actually that's a historical accident by introducing arbitrary temperature scales. So the 1 degree Celsius is 1/100th of the difference between the boiling and the melting point of water. Then they found out about absolute zero and kind of used the same intervals, but with a different zero. But the size of that interval is kind of arbitrary. And actually he argues that if you look at it carefully, the unit of energy, if you see entropy as a statistical concept with no unit, actually temperature should be measured in units of energy. So there's this 1 Kelvin equals 0.13 yoctojoule, I think, which is 10 to the minus 24.
Yoctojoule.
Yeah, yocto. So that's one of like kilo and mega. Yocto is kind of one of the more exotic ones because it's so far off 1. So that's 10 to the minus 24th. Yeah, so then...
It was quite bold, right? To just redefine temperature.
Yeah.
But this is just for one particle, one molecule, the energy of one molecule. So if you have the number, if you go from the molecule to the mole, then you have something close to what we have in mind as macroscopic quantities.
Okay. Could you still say that this Kelvin equates to this average energy per molecule, or doesn't that apply anymore if you go to...
Because the energy is an additive quantity, so you should add the energy of all molecules.
Yeah. And then the average per molecule, would that still be a direct relation?
Yeah, the average per molecule will be that. Yeah.
Yeah, and here's this driving force of change interpretation. Yeah, so then we go into some background about hydrology or applications of entropy in hydrology. So the aim of this paper is really not to derive new results, but kind of interpret and seeing things from a different perspective. I think in my brain, that's still a new result, I would say. So I'm quite happy with reading this paper. Yeah, so we start off by describing entropy as uncertainty. And that's basically based on Shannon's desiderata for an uncertainty measure. So we assume we have a real number that can quantify uncertainty. It should be a continuous function of the probabilities. And if all probabilities are equal, it should be a monotonically increasing function of W. Let's see, I see there's a chat. Yeah, I'll try to, oh, sorry, that was a private message, but I think it's a good idea to try and speed up a little bit and have more time for the discussion since we have the author here. Yeah, so there's this measure of uncertainty. And oh yeah, the last desideratum is that if you group different uncertainties, you should get the same value depending on how you progress through finding out the real answer. So that's this questioning schemes that we sometimes talk about and finding out what the outcome of a die is. So probabilities should add up to 1, of course. Entropy is P log P, or minus P log P to be precise. And actually for continuous entropy, that behaves a bit nasty. So one way to circumvent that is to introduce some kind of background measure, which is in a way also a density. And we can measure the deviation from that. And this is actually one thing I was wondering about, like looking at this, it looks like the Kovac-Leibler divergence. So relative entropy, like I think you say from F to H, but then in that case, the minus sign wouldn't be there. So yeah, we can talk about that later. But I was wondering if this minus sign is essential or whether it's not. So basically, removing the minus sign is the same thing as flipping these two densities here. But that makes it that prevents it from going to infinity. So then once we have defined entropy, we can invoke the principle of maximum entropy. So I talked a bit about that. Basically, whenever you don't know the real probability distribution, you can use all the information you have as constraints, and then subject to that, maximize the uncertainty. And that's the most sensible thing to do, and often turns out to work. So one example here is for a die. Normally, if you maximize uncertainty, you have 1/6 probability for all phases. Then if you introduce some extra constraint that the die is loaded and there's a difference of 0.2 between the probabilities of 6 and 1, and then subject to that constraint, you maximize entropy, you see that those probabilities change, but the other ones are still the same. Or is it are they actually, Demetris, are these still the same as here? Or
no, a little bit change because of,
okay.
Yeah.
Interesting. Okay, yeah, I read it as that this was just for visual purposes, but you're saying it's actually going a bit down.
There is a small change. Everything is affected by loading the die.
Yeah, and then if we have continuous spaces, then it's the oh yeah. So if it's equiprobable, then it just depends on the number of possible outcomes. So W. If it's continuous over a space, it depends on the volume of that space and the background measure in this case. And then let's see. Yeah, so then, so if you don't use any constraints, then the maximum entropy is just the same as the principle of insufficient reason, where if you don't have any other information, you assume all outcomes are equally likely. If you do have some constraints, and often those are in the form of expected values of some functions of the random variable, then you can write it in with Lagrange multipliers and solve it. And that often yields solutions of these exponential forms. So there's the constraints are here, multiplied by some Lagrange multiplier, and then you take the exponent of that, of the sum of all those constraints. And actually, when you look at the most often used distributions in statistics, they almost all turn out to be the solutions of the maximum entropy problem given some type of constraint. So that gives some indication that we're onto something there with the maximum entropy principle. So some examples are, if you just have two bounds, then it's uniform. If it's unbounded from below and above, it's not defined because the probability basically spreads out infinitely. But then if you constrain mean and variance, you end up with a normal distribution. If you have some constraint on non-negativity and you have a constrained mean, you end up with an exponential distribution. And if you end up with a non-negative variable with constrained mean and variance, it depends a bit on whether the standard deviation is lower than the mean. So in some cases it has a solution, and in other cases not. So you tend to have a truncated Gaussian tending to exponential. So if we try to apply that to physical systems, first we can look at the motion of a particle. In those cases, the constraints are, if the particle is trapped in a box and the box is not moving, we have a momentum constraint, which says that the momentum in all directions in total should be 0 in expected value. Otherwise, the box would be moving. And the other one is that the energy content is constant. And actually, there's this equipartition property that says that the energy will spread out over all the degrees of freedom equally. If we then define the entropy for that system, and we try to maximize that, we come up with this distribution, and that ends up to become the Maxwell-Boltzmann distribution. So this is a known result. And let's see. And the resulting entropy is this. So you see, this is a very large constant. Let me see. Or not large in the sense of a large value, but just a big expression. But in the end, this is all constant, and then it depends on the energy content and the volume of the system. Let's see. Then if we extend to many particles, we basically multiply the whole thing by n. And actually there was, and that maybe we can talk about that later. Demetris noted that in classical, the classical equation divides this V by N, and that was based on this assumption of indistinguishability between particles. Yeah, so I would be interested in hearing more about that, why that is a problem, and what it actually means to say they're indistinguishable. Then if you extend to more degrees of freedom than just the velocities, because we're now not talking about monoatomic gas anymore, but gases that can also, the molecules can rotate, then you have to account for more degrees of freedom, but the equations stay the same except for adjusting the degrees of freedom. One question I had there was that can we really see these degrees of freedom just as integers, and like does this equipartition property still apply if it's not just three velocity components, but whether like between velocities and rotation, does energy still split equally between all these degrees of freedom, or are some degrees of freedom kind of more difficult to absorb energy in? It's kind of surprised me that we can just look at the integers. And then oh yeah, then we start talking about temperature, and basically temperature is defined as 1 over the partial derivative of entropy with energy. So that's a kind of generic definition that applies to many different forms of energy, I think. And once we define this new way of defining temperature as an energy, which Demetris calls the natural temperature, then we obtain a very simple expression, which is just 2 times the energy available per molecule per degree of freedom. Yeah, I'll skip over the ideal gas law, but you can see that it becomes very simple in case you use natural temperature. And then this is, I think, the interesting result for hydrologists is that if you think about the Clausius-Clapeyron equation that basically gives the equilibrium between the gas phase and the liquid phase of water in this case as a function of temperature, we basically can think about it as maximizing uncertainty as well, and then derive it only from that. So basically we're saying that a molecule is trying to play hide and seek, and we have to find out where it is, and we can ask questions, and the molecules are configuring themselves in such a way that they maximize the number of questions we have to ask to find out what they're actually doing and where they are. So what they're doing and where they are both applies to whether they are in the liquid or the gas phase, what their position in space is, and what they're doing in terms of the kinetic state. So actually in the gas phase there's 6 degrees of freedom because they can move in 3 directions and rotate in 3 directions, because a water molecule is not symmetric. One thing I wondered about is the fact that it's 180-degree rotation symmetric, whether that would kind of decrease the degrees of freedom a little bit, maybe. That's...
No, I think it is exactly 6. It's very
exactly
consistent with the experiments.
And that's maybe the same answer for this indistinguishability, that the fact that it looks the same when it rotates 180 80 degrees doesn't mean it's limiting the degrees of freedom, because it's still able to do that maybe. But,
yeah, it would be five if the arrangement was linear.
Yeah, because then.
Yeah, but because it is 105 degrees, it has 3 degrees of freedom.
Yeah.
Rotational. Yeah.
Then for the liquid, we assume that the space occupied by a molecule is constant, so the fluid is non-compressible. And for the gas phase, actually, or for the liquid phase, the degrees of freedom is 18 because of what Demetris calls the social behavior of water molecules. So they can kind of organize in some kind of dances where they vibrate in different modes together. And those are a lot of extra degrees of freedom kinetically. So that means you have to basically sink more energy in it to achieve the same increase in velocities. So that's one of the reasons why the specific heat of water is so high. Let's see. Yeah, and then here's the expression for total entropy, which we kind of can recognize from this questioning schemes about dice, that you can ask a question like, is it odd or even? That has a certain entropy, and then when you find that out, so in this case we ask, is it in the liquid or the gas phase? So that's just the probability of being in gas and probability of liquid, and this is just the p log p, right? Sum of p log p. So that's that term. But then once you find out where the water molecule is, in which phase, you still have a lot of more questions to ask to find out what it's actually doing and where it is. So those are these two terms, and they are multiplied by the respective probabilities of being in that. So this is kind of the expected value of the entropy within a certain state, and this is the entropy about the question in which state they are in. And then when you work that all out, you can actually arrive at the Clapeyron equation. It's slightly different from this one, which is the standard textbook one, in that this is kind of anchored at the zero, what is it, the triple point of water, and then some approximation using the Newton-Raphson method. So Demetris argues that this is more consistent, and actually if you look at the solutions, they're pretty similar, but if you look in detail about the relative difference, you can still see quite big departures when you move away from the point where it's anchored.
The points are experimental data, so.
Yeah. And actually, I was wondering, is the variation of the latent heat of vaporization with temperature?
No, sorry, it is the relative difference between the two, but also we have a lot of experimental data from Smithsonian, WMO, etc. So the result is there is a big difference in terms of relative difference of the two cases, and the equation derived here is much more accurate from from what we usually see in hydrology books, etc.
Okay. And I know some people use these empirical equations that are set.
Yeah, the empirical is better than these exponential Magnus type equations are better. but the green blue one is even better.
Okay. Yeah.
Yeah. And easier to use and solve.
Yeah. Yeah. So that's a very nice result, but I think what's even more impressive is what is used to derive it, to kind of start from scratch and then use these very general principles, and then this rolls out. And I find that's often, yeah, the nice thing about working with the principle of maximum entropy is this feeling of emergence, that you put in some constraints, you maximize some very simple function, and then these known distributions roll out. I actually used it once for some ensemble forecasting weighting scheme, and I was not using an analytical approach, but just trying to optimize the weights by maximizing entropy. So it was just like some brute force optimization of 50 different weights, given some constraints using entropy. And then all these nice shapes, like the Gaussian shapes or exponential shapes came out. So in that case, you really, if you're not solving it analytically, it's even more surprising. You can actually numerically try to fiddle with the probabilities to maximize entropy with some brute force optimization, and then these distributions roll out. So that was a nice aha moment for me. So now the question is, if we go to more complex hydrological systems, what can we still say about it? And then the question is, if you don't have similar elements in your system, like all these equal molecules, then it becomes a bit more tricky. And probably we have a bit more uncertainty in the macroscopic behavior because of that. But we can still use the principle of maximum entropy to some degree. And actually what we do see is something similar as in thermodynamics, that on a micro scale, you get this very erratic behavior, and even like in terms of raindrops, they have very, yeah, they're not uniform, they have a distribution. But in the end, if you look at larger scales, you see some simplicity emerge from the complexity again. Yes, then maybe in the interest of time, we can skip this section, but this is about the choice of this background measure. I am a bit wondering, like, is there any guidance for when to use what background measure? I think what I understood from the paper here is that you, whenever you have non-negative variables, you should switch to this logarithmic background measures. But yeah, so in that case, when you use maximum entropy with a single constraint on this quantity here, the Pareto distribution rolls out. That's a heavy tilt distribution. And I think Demetris is arguing that that's more appropriate for many extreme value processes, correct? And one of the reasons for that might be long range dependence that is present in many signals. Oh yeah, and actually the Pareto is quite close to the exponential distribution until you get really into the tail, and then the orders of magnitude basically fly up. So this is very relevant for any engineers working with extreme values. Then, yeah, there's some more results about analyzing hydrometeorological data at a large number of stations and looking at the distributions of those. And like time and again, we see that the Pareto distribution does a better job. And then the last thing I wanted to discuss is this these random points in time where we say some process can give occurrences of something randomly. Then normally you would think that maximizing entropy means that you kind of equally spread out these points in time, and there would be no clustering or no long-term memory processes. But actually, if you include these longer time scale occurrences and you look at the entropy, for example, for a bigger window, if you use it on this series, then the probability of the number of occurrences in each window would be roughly equal. So there's not much entropy in that. While in this one, you would have a higher entropy. And actually, Demetris came up with some formulation where you can maximize the entropy over the whole range of timescales, if I understand correctly. And then the solution to that is actually these Hurst-Kolmogorov processes that tend to have like higher like if there wouldn't be long range dependence, we can see things as a Markov process in which autocorrelation drops pretty quickly. While in these Hurst-Kolmogorov processes, the autocorrelation doesn't drop as quickly, which means we have higher probabilities of multiple wet days or multiple dry days in a row, leading to bigger extremes. So this maybe or probably is connected to this fat tails that we saw earlier. So in general, yeah.
Steven, if you allow me to say one word for this figure that you showed.
This one?
The earlier one. The amazing thing with this graph is about rainfall, occurrence of rainfall, and was a paper published in 2006 in WRR. I used only the blue points, the 2 points for the S constraints, and all the curve was a result of maximizing entropy. And it fits so well the data with only these 2 points as constraints.
Yeah.
Without any other assumption, I mean, just maximizing entropy. 2 constraints, and that's the impressive result. Sorry for the interruption.
Yeah, and that's a good point that in general, I think, and that's what you call the power of this variational approaches such as maximum entropy, is that you put in very little and you get a lot back. So instead of having to estimate many parameters, there's often some structure in the parameters. In the parameters themselves, and that structure arises from this maximum entropy. So if you can pinpoint a few of those parameters, then the rest will fit the maximum entropy description. And actually, maybe I think there's a connection between the sufficient statistics and the constraints you use in maximum entropy. So in a way, maybe that means that there's many processes which have, if you have the right formulation, have just a few sufficient statistics, and then they can produce all basically the whole autocorrelogram so basically the autocorrelogram has a very short, compact description in a way. Is that a correct way of interpreting it, or?
Yeah, but yes, but the sufficient statistics is not a hypothesis, an assumption here. It is, I mean, this approach is more more practical. The sufficient statistics here we do not. We have a different logic. What is the constraint that we know for sure? For instance, when you spoke about the gas in the box, we have only the places of the walls. It's concrete information, solid information, so you put it as a constraint. Then we have the two laws, the conservation laws, momentum and energy. We do not have anything else.
Yeah.
Yeah. So if we put these constraints, we expect to find the exact behavior of the gas, and we do find it. So if there was another law, again, the solution would deviate from reality. So we should look for another law which we did not include in our formulation of the problem. So in logical inference, the constraints are taken from our knowledge experience. But when we describe nature, the constraints are something different. They are the laws that nature obeys.
Yeah.
And we know, we have a lot of knowledge that nature obeys the conservation laws for energy and momentum. Nothing more than that.
Yeah,
so there is no other constraint, and we expect to find the exact solution immediately without trying to find another constraint.
Yeah, but in this case, you estimate two pieces of information from
data. In this case, it is an empirical thing. Yes, in this case, perhaps the solution would not be sufficient. Actually, here the data that we use is what is the probability that 1 hour is dry, and what is the probability that 2 consecutive hours are dry? Because this second information contains the relation between consecutive hours. So,
yeah.
So this is the simplest constraints that one can think. And with this, the simplest constraints, you find a solution that describes very well the data. And you don't have any reason to seek some additional constraints. If you failed, then you could try to find something else.
Yeah.
That's the approach.
But in a way, could we say that that means that implicitly the sufficient statistic for this process is contained in those two pieces of data?
Yeah. Yeah.
Without knowing that explicitly?
Yeah, but without the maximum entropy, the sufficient statistics would not suffice.
No, exactly. Yeah, because
that's my slight disagreement with using the term sufficient statistics.
Yes, I think that
they are sufficient because
it's a maximum entropy.
Maximum entropy, yeah.
Yeah, so sufficient statistics work because the distributions we find in nature are maximum entropy distributions. Yeah.
May I also ask a short question as we are now talking about this point?
Yeah.
So if you scroll up one to figure 9, I found it very interesting to see that some counterintuitive observations that there is clustering behavior on a certain way of viewing the data can be explained by maximizing entropy on another scale. Could you use that to find, say, in a process that the dominant scale of the process is the scale where entropy is obeys the entropy maximization, and the other scales are somehow, dictated by this one predominant scale, and then we can focus on, for example, correctly modeling the process on that scale? Could we use this as an analysis tool?
Can I make a comment on this?
Of course.
Yeah. If there are physical reasons that this is the dominant scale, yeah, perhaps you are right, but usually there are no physical reasons favoring some scales. For example, in hydrology, there is one scale, the annual scale and the daily scale have a physical background. And this you will see in your data and you should take into consideration. Other scales do not exist. I mean, of course, if you go to thousands of years, then you have the Milankovitch cycles, which is another case. But there is no reason that some other thing, some other time frame should be present in your data. So in this case, my thought is that you go to the asymptotic scales. That means as the scale tends to 0, and on the other side, as the scale tends to infinity, and maximize entropy, or better, entropy production at the limits. And you find your law by maximizing entropy both at the left limit and the right limit. And this, in a way, produces the Hurst-Kolmogorov behavior, because you have the fractal behavior on the small scale, which can increase entropy production, but this is about the small scales, the fractal behavior. And then if you go to very large scales, perhaps the graph here will show this.
This one?
The Hurst-Kolmogorov, here is the entropy production on the vertical axis, and on the horizontal axis is the time scale. So the Hurst-Kolmogorov a Hurst-Kolmogorov process has exactly the same conditional and unconditional entropy production for all scales. This is compared here with the Markov process. And you see that the Markov process gives you higher entropy production for small scales, but lower entropy production at large scales. So what would be the reality? I believe the reality should be the red line for large scales. Perhaps a mixture of something. Initially, I thought that the red line could be, and in this paper, I think this I write, that the red line could describe all behavior for all scales, but this is not the case actually, because there are, it is more reasonable to see a behavior that is Markov on small scales and Hurst-Kolmogorov on large scales. This is my, and even worse than Markov in terms of fractal behavior, which gives you even higher. Actually, the entropy production can be as high as 2 in some processes.
Is there some physical explanation for this difference in behavior on the different scales? Or do you have some hypothesis about that?
I have a mathematical explanation. Yes, the physical explanation is that the Hurst-Kolmogorov behavior should give you an infinite variance for S time scale tends to 0. And infinite variance means infinite energy to materialize. So that kind of thing cannot happen in nature for small scales. For large scales, it is fine. And actually, there is a lot of evidence now that the hydrological and geophysical processes follow this, this pattern. But yes, if you actually, I discovered it using turbulence data measured every millisecond. And in this case, we have really very short time scales, and it is evident that the energy, and of course it's reasonable, the energy is finite, and the Hurst-Kolmogorov model cannot describe the small scales. So we have different behavior, different scaling laws for small scales, different one for large scales, and they should be different. Yep. I have another paper about this, this again in the same journal, Entropy, which is called Entropy Production in Stochastics, later than that.
Okay, yeah, very interesting and important as well for understanding many important engineering problems, I think. Yeah, and this was also one thing I thought about that maybe is of interest to this group. So I think this is, in my opinion, it's a bit related to this sufficient statistics that, or maybe in some way to minimum description length that you can, that actually many processes can be described by a few parameters instead of many, as long as you have this maximum entropy hypothesis to help you estimate the rest. It basically gives a unique solution to an otherwise indeterminate problem. And I was wondering if that would potentially help in machine learning somehow, where maybe we're trying to estimate many parameters, but maybe there's some hidden structure in those parameters that is kind of revealed by maximizing entropy given just a few constraints. But that's just wild speculation at this point. Let's see. Yeah, this is some example of why these complex processes in the end act very linearly if you go to the right scales. Yeah, so going to the conclusion, I think Demetris showed that that entropy in any form can be seen as a form of uncertainty quantified, and the fact that that tends to become maximal is not a big problem, because usually we're not worried about the microscopical processes, but more on what they mean on macro scale. And actually this unpredictability on micro scale helps predictability on the macro scale that we have to deal with. And yeah, there's many different physical laws that we can derive from it, but also it helps us in finding stochastic descriptions for processes. So this is an interesting point, that going more into the statistical thermophysics, the hydrology, and the kind of database descriptions using maximum entropy, if we can somehow unify those, we probably can find some more interesting things. Yeah, so that's all for me. I think I've talked way too much, so I'll shut up for a while and see if anyone else has some discussion points to ask Demetris. I'm still available to help scrolling to desired figures or pages.
Maybe one general question, Demetris, in the community in which Axel Kleidon and Roderick Devar and others work, I often see that maximizing entropy production as an optimality principle is the holy grail, and hoped for that it will solve a lot of underdetermined problems, which I think it has the potential. But often the devil is in the details about which constraints to correctly assume. In all the examples you gave in the paper, which I find really great, they were correctly chosen and completely describe the framing of the problem. Do you encounter this problem in general too, that sometimes it's just impossible to find the right constraints, or do you find that problem not so pressing? Your microphone is still off.
I'm not sure if it is the Holy Grail, because many people debate that, and they say that there is no such principle in nature, that maximum entropy production. So I believe there should be, because you see the standard entropy formulation, like described in this paper, the time is absent, and there should be time in physical laws. So whether this can be formulated in like a derivative in time, or in a integral form somewhere, again including time, is not an issue that has been concluded. I believe people search right now how time could be included in the formulation of the dynamics of the system in terms of entropy. I believe there is no agreed formulation of the problem. Myself too, I use the derivative, but perhaps it's, the frame is more formally probabilistic. Mine, I try not to use anything from classical thermodynamics unless I derive it probabilistically. Of course, this is not something that I would advise someone else, but yeah, one could try to do this way. You allow me to do this way to see if it is effective. And in those problems that were presented by Steven, I believe it is effective. I have some plans next year where I will be retired to continue this research because nobody funds it. So I believe all these problems are open, and there is a lot of research for someone interested to do.
I had one question for this this last process where you use this logarithmic time. Is there any particular reason why logarithmic time should be chosen? It works better, but I wonder if there was any motivation beforehand. to choose that?
First of all, if you notice this paper, in all cases, I try to have dimensional consistency, even in the definition of entropy, which is not always the case in text about entropy. For instance, if you have the logarithm of the density function, this is mathematically correct, physically is incorrect, because you cannot take the logarithm of a dimensional quantity.
Yeah.
Okay. Now, entropy is dimensionless quantity, at least in the statistical framework, and you have already discussed that. So if you take entropy divided by time, this is a dimensional quantity. So the derivative is dimensional. But if you take the logarithm of in terms of logarithmic time, it again becomes dimensionless.
Oh, okay.
One thing is this. The other thing is that if you maximize the entropy with respect to time, then this maximization is also valid for time. So there is no difference in the state that maximizes the derivative with respect to time or with respect to the logarithm of time. So I prefer the second, for this reason, I prefer the second case with respect to the logarithm of time, which has some dimensional advantages and also graphical advantages, because this derivative with respect to time is the slope in a log-log plot.
Okay, yeah. That makes sense.
More practical, yeah.
Any other questions for Demetris?
Can I ask a question about figure 10 again?
What is this? Can you still?
So yeah, so the data points. So that the two blue diamonds, or it looks like it's not. It's not two blue diamonds, but there are a number of them superimposed, right? So I guess my impression was that this is two observations, but it's a number of observations about a specific time scale. Is that correct?
Yes, there's 70 years of observations. And from these 70 years, we calculate the probability dry for 1 hour and for 2 hours. And these are the diamonds. The scale is denoted as K. P is, means probability. So it's something very close to 1. It's for Athens, you see. In Athens, rainfall is not very frequent. So the probability dry is close to 1. So we get just these two probabilities for 1 hour dry or 2 hours dry. 2 hours dry means either one of the two are dry. Oh, sorry, both are dry. Sorry, both hours are dry. This is not the product because they are.
Okay. So I guess my question is.
Yeah, of course, you know better than me what the question is. Perhaps I didn't understand.
Oh, your sound.
Well, my question related to that is, I guess I'm curious. So I understand this is 70 years of data. Sorry, can you hear me okay? Is that, oh, hello? Okay, sorry. My question is, you know, so the two timescales, the 1 hour and the 2 hour timescale, were used to create this model for you know, this entire range of timescales. But it uses the entire record for, you know, for these two timescales. So what would the effect be of, say, a much shorter, you know, say the two timescales being estimated based on a much shorter interval within the 70 years? Yeah, I guess I'm wondering what the relationship is there in terms of the length of record. What, you know, what if you have 2 years versus 70 or versus 200?
This is yeah, this I haven't done this exercise anyway, but I guess the if you separate the 70 years to, let's say, 35, if you use 35 samples, some sub-samples of 2 years each, then you will have a range of variability, because the probability dry should not be the same in each of them. Okay, so this is an issue of estimation. Your estimation, if you have 70 years of data and you want to estimate the probability, whatever probability, it is better to use the entire set of data. The problem you are asking, you are putting is interesting, but I haven't examined what would be the variability of the estimates in terms of different probability estimating for its case. I haven't, because here the objective was to see if, using the entire information, but only 2 timescales, if it was possible to find for several orders of magnitude larger timescales a correct prediction. And it seems we can't do that. That's another problem. Perhaps.
Thank you.
May I make a comment on Steven's presentation, because he said something about the chamber with a wall in between, and then moving the chamber, etc. Yes, of course, the maximum entropy framework with those constraints should work in both cases. When we have the gas in the one chamber, in the small chamber, or in the double chamber, it will work. Now, it won't work for some milliseconds, as you said. You cannot predict what will happen. So, because in this case, time becomes important. For those milliseconds, you need another formulation. I believe, again, the maximum entropy, maximized in some way, for instance, in terms of derivative, maximum entropy production or something like that, should work. But you need also other constraints. That is my feeling. I haven't done that.
Yeah.
And also you mentioned about the indistinguishable particles. Oh, yeah. I have another paper about this. I don't believe that the particles are indistinguishable. And there is no need to make such an assumption. Although this is a very popular assumption in physical thermodynamics books, I believe it could be it could work without this assumption. And I think it works better, because if you have the volume per particle, like as you said, then you will have the same entropy in terms of if you have half mass of air in a smaller in the small chamber, or if you have twice the mass of air in a double, you will have the same entropy. This is not reasonable, because the position of the particle in a bigger space is more uncertain. So you should have a bigger entropy. That's why I don't believe that the particles are indistinguishable. And I have done some contribution on this. Yeah, I could make the same results as Sarcourt with an entropic, a formal entropic framework. But in this case, what is called entropy is not actually the entropy. It is the difference of two entropies. And this also explains the so-called Gibbs paradox.
Okay.
Now, whether one final point that I noted, you said whether the degrees of freedom are integer or could also be real. I believe in simple cases, they should be integer. And the simple case that I have in mind is the gas. The gas is a very simple case because it is atomistic. Any molecule is dependent of the others. If we have more complex cases, like in liquid water, then we have the social behavior, the links between the molecules, and then I believe you can have a real number of degrees of freedom.
Okay, yeah.
That's my view anyway. Not sure, but again, if you see the solution, there is a slight difference in terms of the optimal coefficient, and those are the optimal based on data, a very small difference. It is 5, the difference of degrees of freedom is 5, I think.
Yeah, like 5 versus like, 5.06, or?
Yeah, no, if you go to the final solution, it's like, if you, a little,
this
yeah,
one?
yeah, it's 5.6. The experimental value is 5.06. But if you go to the analytical solution with 18 degrees of freedom, it's 5, exactly 5. So this means that the average degrees of freedom in the liquid phase is not actually integer, is real. It's something more than 18.
And would that be related to like energy more easily going into some of those modes versus others, or is it maybe some kind of fractal behavior of
a statistical average, because each molecule may have different number of neighbors with which it connects.
Okay, yeah. Yeah, that makes sense. Any other questions? Uwe?
Demetris, do you have an idea how we could best combine, say, stochastic modeling based on, for example, maximizing entropy and classical time step per time step fixed spatial resolution environmental systems modeling? You know, if I look at your results, it would make no sense to model 10,000 years of a system just to find out what its 10,000 year behavior is, but still we would require some spatial and temporal resolution of the results. Do you have any idea how we could combine these modeling approaches?
I think that the first thing in order to make a correct model is to formulate it in continuous time or space, and then infer the behavior in discrete time from the model. And also this means that when you involve time, then it is better also to use the derivative, the entropy production, coming back to what we discussed before. So I think this is a very interesting problem, and I think I have some contribution on this. And my final reply is this: work on continuous time, and then see theoretically and prove what is the discretization effect, and include it in your model, in your estimation, because the discretization also adds some bias in your estimation. You should consider that bias. So, but this can be inferred theoretically with mathematics. So you formulate initially the model in continuous time, and then you get everything in discrete time in whatever scale you wish. I'm not sure if I correctly interpreted your question. Perhaps you asked something else, or is it?
No, it's fine. I get an idea.
Okay.
Thanks.
So maybe one question for Demetris: are you still is this still your main interest in your current research? Because I realize the paper is a little bit older, but
yeah, of course I'm very interested. The problem is that I don't have time, and I was involved in some other issues for random reasons, not because of my willing, but for random reasons. I was involved in other issues. And as I said, next year I'll retire, and I look forward to work further on entropy. And I am also, I will be happy to collaborate with any of you on such issues. And by the way, I had discussed with Uwe a case that a special issue was invited by the journal Entropy, and you did not have time. But if you have a paper, I found a Greek colleague who agreed to take the responsibility for that special issue. A couple of Greek colleagues. And so they will materialize, and if you have papers on entropy, they will be glad to receive and process them.
What's the topic or title of that special issue?
It's about entropy in water cycle, something like that.
Okay, yeah.
The journal is good, actually. It has a good impact factor. It has, I have published 2 papers, one rejected, which is good.
Yeah, there's a few very interesting papers in there for sure, including this one.
Yeah, I don't want to advertise this, but I like they have some interesting good things, this MDPI, although some criticize it as just they work only for profit, which perhaps could be true. But they also have a very fast reviews in 1 week. They fast decisions, and I like also that they put everything online, like the journals of EGU, but after the review, they put the reviews online, which I like. I want everything to be in public, not hidden. So I like those issues, those features of this MDPI, I think.
Okay. Is there still anyone with any questions for Demetris?
There are some in the chat, I think, but perhaps there are no.
Yeah, some
yeah, those are some final announcements of the session, but if anyone has a question, we can follow with the questions.
Okay, may I repeat that I'm very honored for the choice of my paper of your group. And I thank you very, very much, particularly Steven. I liked very much his presentation of my work, and this is another honor for me. Someone presents my work. I didn't have before that feeling. So thanks to everybody. And I wanted to say something more, but perhaps, yeah, it's fine.
Yeah, I want to thank you very much.
Yeah, just for gossip. Only one guy had made me comments for this paper, and this is Hubert Savanier.
Okay.
Because he liked the proof of the Clausius-Clapeyron equation. He saw that and he wrote. Otherwise, it is not a popular or highly cited paper or whatever. Even though I believe it has a good title, but I think it remained unknown. So yeah. It is for this reason, I'm even happier that you have done this event today. Thank you again.
Yeah, thank you very much for being able to join at this late hour. And I must say I felt quite nervous presenting your paper, and I was quite severely time constrained, so I hope I didn't make any stupid remarks about it. But no, fortunately, we're
much better than I would do. Much better.
Yeah, so I give the mic back to Leila, I guess.
Sure. If there is no other question, I also want to thank you, Demetris and Steven, for the great presentation and the contributions. And I will make an announcement for the next session. So in the next session, we are asking for a volunteer to co-lead the session. So we are going to be discussing the paper, Understanding the Information Content in the Hierarchy of Model Development Decisions, then learning from data. And Shubhran is going to be leading the session, and we want to ask for a volunteer to co-lead the session if there is any. So besides that, I want to thank you everyone for joining today. And I don't know if anyone has any other comment or announcement to make to the group.
No, I also wanted to thank Demetris. I mean, it's great to see you after a while, Demetris, and thanks for all the thoughtful work you do, not just this paper, but some of the other papers that I've read. So this is wonderful to be able to look at this work. I'm still trying to figure this thing out. It's pretty detailed, so well, working through that.
Yeah, and I also wanted to say that this topic is really important. And I think it was one of the first questions that I asked Professor Kumar during his class, like what is the relationship between entropy in thermodynamics and in, so I am pretty sure many students and many people in general are wondering what is this about, and this is a great paper to investigate that. So
Yeah,
thank you.
I'm going to include it in my reading list for the class now.
Yes, great.
So the citations will finally start coming then, I think.
So this question should be valid for the next 100 years. So you can ask this question because it's a difficult one. So it's not embarrassing to ask such a question now and in the future.
Yeah, the fun lies not in answering the question. The fun lies in actually the process of answering the question, right? I mean, that leads to some very interesting things. So there's still a lot to be learned in that regard.
Okay, thank you, everyone.
Thank you. Thank you.
See you in the next session. Bye.
Bye.
Thank you very much.
Thank you. Bye.